Hi, in this video we're going to go through some worked examples solving approximations of real-world problems using tools of projections, least squares. Let's begin with a problem on office workload. A municipality, a city, has 2 offices handling construction permits, and every week the main office is able to process 600 applications, 300 inspections, and 120 complaints, while the branch office can handle 400 permit applications, 100 inspections, and 80 complaints. If there's a monthly demand of 2,000 applications, 1,000 inspections, and 800 complaints, how many days or weeks must each office work to best satisfy the demand? I will give a hint that this is not a problem that is perfectly solvable. We will have an approximate solution. Is the solution a good one? And how would this change if the complaint load was reduced by 50%? I recommend that you pause, try to solve the problem to the best of your ability, and then resume to follow the worked solution. We always begin a problem like this formulating the mathematical model. Define our variables, our unknowns in the problem. How much is each office going to work? We let x1 and x2 be the weeks worked by the main and branch offices, respectively. The question actually asks for us to find things in days in the end, but the data is provided in weeks. Let's work in weeks, and we can always convert to days after the fact. Once we have the variables defined, we have to write out our equations. We'll have one equation for each of the types of action in the office, one equation for permits, one for inspections, one for complaints. And in each case, our right-hand side is going to have our total demand, and our left-hand side is going to have the amount handled of that type for each office. 600x1 plus 400x2 equals 2,000 as an example for the permits. Then the equation for inspections, the equation for for complaints. Okay. Once we've done this, we take a look at this expression, and it looks a bit messy. We have hundreds, thousands. It's always a good idea, especially if we're working through a problem by hand, to at this point simplify the system as much as possible. The first equation can be divided by 100, and that would give us 6, 4, and 20, and then could even be divided through by another 2 to give us 3, 2, and 10. And so essentially we have a scaling factor where we've divided by 20 divided by 200 this whole equation to give us a simplified version. The second equation can be divided by 100, giving us 3, 1, and 10. And the fourth equation can be divided by 40, giving us 3, 2, and 20. And that's as far as we can simplify things, but this takes us down now into a system where the numbers are small and manageable. This doesn't change the final answer in any way, although we will need to remember perhaps that we've done this scaling if we want to relate things back to the original numbers. It doesn't change the solution in any way, but it simplifies the arithmetic. Okay. Now, how are we going to go about and solve this problem? Note that we had an approximate problem. I've told you that this doesn't have an exact solution. The problem was also phrased with asking what is the answer for one set of demands, and how does this change if there's a different set of demands. This all suggests that we ought to solve this problem with the approach of a pseudo-inverse. Remember that a pseudo-inverse allows us, as long as we have a full rank matrix, it allows us to solve for a solution, giving us the least squares, best approximate solution if we have an inconsistent right-hand side, or a right-hand side that gives an inconsistent system, and gives us our exact answer if there is one. Give us a general way to deal with non-square but full column rank systems, which is what we have here. We can see that that's what we have by translating our system of equations into matrix form. Our coefficient matrix will have two columns, one with all threes, one with 2, 1, and 2. These are clearly not scalar multiples of each other, not linearly dependent. Therefore, we have full column rank, and our right-hand side here. Now that we know an approach that should work, we go through and execute on it. We need to calculate this pseudo-inverse, and we're going to do this with a three-step process. First of all, calculating the product A transpose A, then computing the inverse of that product, and finally computing the product of that inverse with A transpose. Now let's work through that. A transpose A, A transpose, and A written here, multiply using standard rules. 9 plus 9 plus 9 is 27 for the first element. 6 plus 3 plus 6 is 15 for the second column of the first row. The third row gives us 6 plus 3 plus 6, 15, and 4 plus 1 plus 4 is 9. We note that this matrix is symmetric, as it should be. Always good idea to double check that our answer to this is in fact a symmetric matrix, as it needs to be. Once we have A transpose A, we can find its inverse with Gauss-Jordan elimination. We set our A transpose A as one block, our identity as another block, and simply carry through elimination. First pivot, eliminating downward. We could scale these in a first step if we wanted to, recognizing that we can divide this top equation by 3 and the second equation by 3 as well. But we can also just work with these. The scaling factor for elimination would be 15 over 9, or sorry, 15 over 27, which is which is 5 over 9, as we see here. So we subtract 5/9 of the first row from the second. 27 minus 27, of course, gives us 0. 9 minus 15 times 5 over 9. 15 times 5 over 9 is 75 over 9. And 9 is, of course, 81 over 9. So we have 81 minus 75 over 9 gives us 6/9. Little bit of messy arithmetic in calculating this, and you can always write it down if it simplifies. but it doesn't give us too messy of a final answer. 0 minus 5/9 of 1, of course, is negative 5/9, and 1 minus 0 remains 0. Once we have this second row, we can scale this row by multiplying by 9/6. This will give us 1 in the pivot position, 5/6 in the first column of the identity block, and 3/2, because of course 9/6 is 3/2, as our last entry. Once we have this, we can eliminate upwards. We subtract 15 times this last row from the first. The 15 minus 15 gives us a 0. We have 1 minus 15 times 5/6. Well, the 15 can cancel out with the 3 of the 6, giving us minus 25/2. 1 minus negative 25/2 is 27/2. 0 minus 15 times 3/2 is negative 45/2. These fractions look a little bit messy, but when we divide through by scaling by this pivot, divide through by 27, we get a 1, we get a simple 1/2, and this becomes 5/6. We're essentially dividing through by 27, which is 9 times 3. The 45 divided by 9 gives us 5, and we're left with the 3 times 2 gives us 6. Second time to give a check. This is our inverse. We have our identity block, and thus this second block is our inverse. It should also be symmetric, and it is. This is a good double check on arithmetic errors, making sure that that we do in fact get a symmetric matrix. You can also always test this against the original matrix if you want to be sure that you correctly calculated the inverse. Now that we have A transpose A inverse, we are ready to compute our pseudo-inverse. We multiply our result by A transpose. To simplify things, I'm going to pull out the 1/6. The inverse that we had computed was had all of these fractional values, sixths, halves, and so on. It often simplifies things to factor out the fraction, leave this outside of the matrix, and have whole numbers inside that are easier to work with. When we've done this, then we just have whole number arithmetic for calculating this matrix product. Leave the 1/6 there. 9 minus 10 is negative 1. 9 minus 5 is plus 4. 9 minus 10 is negative 1. Negative 15 plus 18 is 3. Negative 15 plus 9 is negative 6. And negative 15 plus 18 is 3, with this 1/6 in front of it. Right? This is our pseudo-inverse. I'll leave it with the 1/6 and only deal with that multiplication by the fraction when we need to at the end of calculations. Our original system is shown here. Our right-hand side was 10, 10, 20. We are now ready to compute our answer simply by multiplying this pseudo-inverse by that right-hand side. Negative 10 plus 40 minus 20 is 10. 30 minus 60 plus 60 is 30. Now we multiply through by the 1/6, and our final answer is 5/3 and 5. Now we can take this answer and interpret it in the context of the original problem. Remember that these two variables were x1 and x2, that weeks needed to work by the main office and the branch office. The main office needs to work 1 2/3 weeks. So depending on whether we're going to count this as a 5-day work week or a 7-day week, wasn't specified in the problem, somewhere between 8 and 12 days overall. The branch office needs to work 5 weeks, again depending on how we count these, somewhere between 25 and 35 days. Already, this looks like a problematic answer. At least the upper end of this goes beyond the number of days in a month. So this is both an unbalanced solution. The main office is working much less than the other, but also the amount of time being asked to work by one of the offices seems to be perhaps violating the number of available days, or at least very close to it. We can also evaluate whether this is a good solution by asking how close is this approximate solution to the desired solution. We do this by plugging our computed solution back into AX. This is just a matrix multiplication, not solving a system. A times X is 5 plus 10, 15. 5 plus 5 is 10. 5 plus 10 is 15. Here we remember that in our original problem setup, we scaled these. We scaled the first row by 20, so multiplying that, by 20 by 200 gives us 3,000. We scaled our second row by 100, giving us 1,000, and we scaled our third row by 40. This converts us to 600. Right? These are quite different than the actual demands for the permit applications and the complaints. Our error vector, found by taking our actual right-hand side compared to our target right-hand side, gives us an error of 1,000 more permit applications than we wanted to handle, and a deficiency of 200 complaints. That is a 50% error in one term, a 25% error in the other direction on the other term, and one that is perfectly matched. This isn't a great solution. It's not completely terrible. It's not orders of magnitude off and grossly violating the constraints of time, but it has a fair bit of error and not an ideal match to the actual number of available days. How would this change if the complaint load was reduced? Right? So one of the things that you might see in here was that the deficiency, the place where the offices could not handle enough, was in the complaints. Right? If we reduce the complaint load by 50%, how would things change? Well, here all we're doing is we're taking the complaint entry of the right-hand side and dividing it by 2. We can do this in the scaled form because we have a percent error, so we can just divide this by 2 and then resolve the system. Plug this new right-hand side back in with the same pseudo-inverse and we get negative 10 plus 40 minus 10 is 20. 30 minus 60 plus 30 is 0. Multiply by the 1/6 gives us 10/3 and 0. Once again, this is our x1 and our x2. The main office should work 3.33 weeks, 17 to 24 days, a very reasonable number for a month. And the branch office actually doesn't have any work here. If we test this solution in the context of the original problem, 3 times 10/3 is 10, plus 0, 10 plus 0, 10 plus 0, we get back our exact right-hand side. These match, we have an exact solution. Remember, the pseudo-inverse will give us an exact solution when there is one. So this is not an approximate solution, there is no error, and it's a very clean solution with a reasonable number of days. So an example with a problem that really this falls into the class of an industrial sort of production problem. We're trying to balance resources, in this case the labor resources of a city office, with demands upon those resources. But in a case where we need to use least squares solutions, pseudo-inverses, to solve the problem. Now let's take a look at a second example. On this problem, we're looking at a regression problem, trying to fit polynomials, fit lines to a set of data. I want you, in this case, to set up the problem, but not to solve it. These regression problems are almost always difficult to solve by hand. They have a lot of real data, is typically messy, not something you want to work through the arithmetic on paper. They're best solved computationally, but we can at least see how we should set up this problem. And then if you wanted to solve it, you can plug it into MATLAB or something like that. So set up, but do not solve, a set of regression problems for a data set shown here. This is data comparing earnings between generations. So the average income of parents grouped according to various income levels, and then that's compared to the annual income that their children ended up earning. There is data out here that looks like this. These numbers are completely made up by myself. These are not actually data from a real source. How would we look at possible relationships between these data using regression? Can we find a best linear fit? Y equals mx plus b. Can we find a best linear fit that has to go through the origin so that 0 matches 0? Can we find the best quadratic fit? Can we find the best quadratic fit through the origin? And in each case, we want to get an expression that will give us the parameters of the fit, for example, m and b, and for the total squared error. And we want the parental income to be the independent variable, that is the x's, and the children's income to be the dependent variable, the y. I recommend you pause the video, try to set these up on your own, and then resume to look at the worked solution. all of these are going to take the same general approach, building a regression model based on least squares solutions. Given a set of data, paired values of a dependent variable x and an independent variable x and a dependent variable y. This second one ought to have had a subscript of 2 here, of course. So some set of data and a target model where we would like to reproduce the y's as a polynomial in terms of x. That is, some constant plus a constant times x plus a constant times x squared, and so on for as many values as our order of polynomial we want to fit. For a linear fit, we would end after the second term. For a quadratic fit, we would end after the third term, and so on. But the general form for solving this kind of problem is that we build a matrix that has columns whose entries are processed values of x. So the first column has all of the x values raised to the 0 power. Of course, that actually just gives us a column of all ones. The second column would have the x's all raised to the first power. The third column would have them all raised to the second power, and so on. And if we do this, construct such a matrix, the attempt to fit this becomes A times Q equals Y, where Y is a vector of the Y data from our data set, and Q, our unknowns, are the parameters of the fit, the coefficients of this polynomial. And we find this with a least squares solution of pseudo-inverse multiplied by y, where the pseudo-inverse of course is A transpose A, all inverse times A transpose. A standard least squares solution to an inconsistent linear system. So really the problem we're going to have for each of these different types of fit is going to be constructing A in the right manner. Let's start with our best linear fit, y equals mx plus b. Y equals mx plus b, to rearrange it into our standard form, would be y equals a0 plus a1x, where a0 corresponds to b, our constant, our y-intercept, and a1 corresponds to m, our slope. The structure of A would have a first column corresponding to that 0th order term. The x is raised to the 0 power, a column of all ones, and the second column of A would just be all of the x data as a column to the first power. The y would be our set of y data, and given this A and this Y, AQ equals Y is our linear fit, where Q holds our parameters, A0 and 1 in the general form, or B and M in this more traditional way of writing the linear fit parameters. And we are going to find this simply by taking A transpose times Y. This is all we need to do for setting up the problem. We've said, we've defined all of our matrices, our vectors, and we've given an expression using those that would give us our parameters of our fit. How would we assess the quality of that? We might look at the error. The error, if we want just a single number to describe the error, we can get that by looking at the norm of the difference between the actual answer and the target answer y, and the actual answer, which is given by A times Q, where Q is A pseudo-inverse times Y, so the error A pseudo-inverse Y minus Y. Take the norm of that difference, and it will give us an estimate of our error. This was for a linear fit. How do we handle a linear fit through the origin? The only thing that is going to be different is our definition of A and the Q, which holds the parameters. If we have a linear fit through the origin, B equals 0. That means we already know that coefficient. We do not need to solve for it. Our target model then is just y equals a1x, where a1 is, of course, our slope. That means that our matrix A only has a single column that has the linear values x in it. Y is exactly the same. Q only holds a single number. It's actually a scalar that has that slope. However, although this seems like a very simple problem with just a single column for our matrix A, we can still solve it in the same standard way. Define a pseudo-inverse, compute the coefficients by multiplying that pseudo-inverse by our right-hand side, and compute the error in exactly the same way. What would a quadratic fit be? Our quadratic fit, ax squared plus bx plus c, if I rephrase this in the form that I had presented as a standard, a0 plus a1x plus a2x squared. This kind of just reverses the order, putting our constant and then our linear and then our quadratic term afterwards. When we do this, our first column, the 0th order term, is again a column of all ones. Our second column is the linear term, the column of all x's. And we have a third column now that has all of our x values squared. I'm just going to leave them squared rather than actually trying to evaluate those here. The y is exactly the same. Our q holds our parameters of our fit, the coefficients in front of this quadratic expression. But otherwise, the process is identical. Pseudo-inverse multiplied by the y gives us our coefficients. Our error is given by the same form. Finally, quadratic fit through the origin. Here, our constant term is 0. We can write this as a new model, linear piece and a quadratic piece, but no constant. How does that change our definition of our matrix? We delete the columns of all ones which corresponded to that constant term. A column of x, a column of x squared. We can compute a pseudo-inverse from that matrix, use that with our column of y's to get the parameters of our fit, and the error is the same. These four examples, highlight the basic process of how you use regression to solve a problem. The method is always the same. Compute the pseudo-inverse, multiply that pseudo-inverse by the dependent variable target, and that will give you the coefficients, and you can compute the error. What changes depending on the type of fit, linear, quadratic, cubic, or so on, constraints of going through the origin or or so on, those all factor in only in how we define the matrix A. Okay. So those were two examples. One, a application that gave rise to an inconsistent linear system that we could solve using a least squares approximation. And the second, an example of fitting data to linear and quadratic expressions using the same ideas of least squares, but in a different framework. In the homework, you'll have more opportunity to practice with these kinds of examples. Thank you, and goodbye.